Hello, folks. Welcome to the next episode of Lagrangian Mechanics Masterclass. I'm your host, Refath, and today we're going to go through several examples of Lagrangian mechanics in the world. So today I'm joined by my guest, Soborno Isaac Barry. Let's take a look at what we have to say. So, Soborno, would you like to give us a brief overview of what we did previously?
Last time we derived the Euler-Lagrange equation using principle of least action, and based off the principle that the Lagrangian is a mechanical quantity that can be expressed as the kinetic energy minus the potential energy, written as T minus V. We derived the Euler-Lagrange equation, which can be used in tandem with the Lagrange.
Okay, perfect. Now, speak anymore, you're going to bore the audience. How about you share your screen and show us some of the simulations that you've got on there?
Just give me just 1 second or two. I'll switch tabs really quickly. So let's see. So do you all see this?
Yeah, wow. So what is that? Can you reload the page so we can
yeah, so that is supposed to be a double pendulum. Yeah, that's how there are way too
what if you click show energy? The show energy button over there.
What show energy? Oh.
Let's see what happens. Okay, so the total energy should be conserved, right?
Yes, the total energy is about 3.23.
Wow.
It's because of either some damping properties, which is why it's constantly decreasing.
Okay, cool. What if you like change the parameters like gravity, mass to
Of course, gravity, it becomes a little more chaotic.
Okay.
If you make it 0, the first pendulum barely moves. It's only pulled by the gravity of the second pendulum. And you can see that because if I do this, then I let this be 0.
Wow, that's fascinating. That's fascinating.
See this?
Can you show like what happens when you actually move the first pivot? Like bring gravity back to normal and show us what happens when you move. Just move around the first pivot a little bit.
Oh, this one?
No. Like take your mouse and move the blue pivot.
Oh, you can do that?
Yeah.
Oh, okay.
Wow, that's cool. Okay. Can you show us the spring pendulum that you have on the third tab?
Yep.
Okay, what's this about? Can you click start and show us what's going on here? Explain.
So here we just have what seems to be a spring.
Okay. Yep.
Now, yeah, we can show.
Okay. But this isn't a normal pendulum, right? This is a pendulum, but instead of a rope, you have a spring, right?
Yeah, it's just a spring.
Right. Well, it's just a spring. It's a vertical spring. And a rope is nothing more than a bunch of springs. You want to say something?
The simplest systems, no?
Yeah, you're right, actually. Yeah. What about what have you got there? Can you change the parameters on the left? This one is a little slower, but yeah, change the parameter, wait a little bit. It doesn't update. So that's a spherical pendulum. Yeah.
Stimulating enough. Oh, this one is a conical pendulum, which is another less commonly studied system. You'll see this not so often in AP Physics and beyond.
Okay. Can you change the parameters around? What if you change the rope length? What happens then?
If you change the rope length, well, okay, it's been a long time since I studied AP Physics, but
interesting.
Of course, we have the centripetal force over here. T sine theta acts as our centripetal force. T cosine theta acts as the opposing force to mg, but not the action reaction force, obviously.
Okay.
So we can fast, super slow.
And what about the last simulation you have of a block sliding down an inclined plane? Could you give us some motivation about that? That's the last tab you have.
Dumb thing.
Block sliding.
How do I?
Yeah.
What's this thing on top of that? I don't know how to hide.
Oh, I see. Let me see if I can. Yeah, there you go. So can you go ahead? Tell us what this is about. Click the play button on the lower left and then explain.
This is very clearly just the block sliding down an inclined plane. Obviously, there's some friction involved. Now, if you read this to be like really, can we restart this? Yeah. So if we like read this to be really large, then the block will barely start. If we make this super large, like 1.1, which shouldn't be possible. I don't know why it does that.
Okay, that's interesting. So now, now that we've gotten to kind of intuitively see a few of the systems we're going to analyze, let's jump. Yeah.
Not moving anymore.
Oh, there you go. Okay.
Yeah, until you raise the.
I see. Okay, maybe it has a bug. I mean, it's a simulation after all, so you never know. But it seems like your mu sub x is greater than 1, which is not possible. Yeah, there you go. So now we're gonna start getting into the math. So why don't you stop sharing your screen? I'm gonna start sharing my iPad.
I have your math right here.
Yeah, but that'll take longer to update. So stop sharing on your end. And
stop. Okay.
Yes. So let me share my screen here. By the way, I should mention one of our viewers just said, Snee Rock said, just go and sleep. To which I answer, no, sir. We will continue doing physics until. Okay. Did not have the best response to come up with there, but
I think it's because it's midnight in India, so people think it's midnight for us as well.
Yes. Well, midnight, daytime, regardless, it will not stop us from doing physics. So let's take a look at the spherical pendulum that you explored there. I'm gonna let you be
the double.
The double pendulum.
Yeah, the one on the previous slide.
Yeah. Which one do you wanna start with?
The double pendulum.
Okay, sure. So, we have another comment from our viewer by Dayam. I guess it's day in their time zone. So, okay, let's start with the double pendulum since that's what you wanted to start with. So I'm going to erase this picture and just draw it nicely on the left-hand side.
All right.
So while I'm drawing it, can you explain a little bit about what the double pendulum is to the viewers?
So the double pendulum basically. Oh, okay. Sorry. So the double pendulum is basically, here we have one pendulum on top of another, and usually, let's.
Don't draw on the Jamboard. Just close your Jamboard. That's causing some problems on my end.
Oh, really? It is?
Yeah, I just had to reload the app. So, please don't write on your end.
All right. That makes things a little less interesting, but sure. So this right here is what's known as a chaotic system. So it seems it's very hard to analyze with Newtonian because we don't have just one pendulum, but also another pendulum, which is using the first pendulum as basically its rooftop. So it's as if we have a pendulum. Oh yeah, and the second pendulum also affects the motion of the first pendulum. So things get very chaotic very quickly. So yeah.
Exactly. So that's a good definition. Yeah. There's M2 affects M1, M1 affects M2. There's gravity. I mean, it's a headache to do with Newton. So we've got to use Lagrange. So first and foremost, we're going to have our guest, tell us what the Euler-Lagrange equation is.
Okay, so the Euler-Lagrange equation is precisely, I really wanted to write it down, but that's fine, partial L over partial X is equal to d dt. Oh, shit. Okay, sorry.
Do you see what I'm writing, or what are you? Oh.
I do see what you're writing, but you might not see what I'm writing. That's kind of...
Again, that's going to cause a problem on my end. So, as you can see, it's written over what I've written, right? So
yeah, that's not good. But I've already written the rest of the Lagrange equation, which is partial L with respect to x dot.
Okay. as you can see, it doesn't look like anything. So don't write on your end. Just let me know what I should write.
Really? Okay, that sucks.
So this is the Euler-Lagrange equation. Please don't write. So what should I have after this? What is my Lagrangian?
The Lagrangian is T minus V, or kinetic minus potential.
Kinetic minus potential. What should my kinetic be?
Kinetic energy in most scenarios is half mv squared.
Half mv squared. Now think about this. Let's think about this together. How many masses do we have in this problem?
Here we have not just one, but we have two. So that's going to cause some complications.
Exactly. Okay, yeah, you can write a little bit, so that's fine. Just don't write the equations. I think that's going to be a hassle. Yeah. I see. Yeah.
You erased your Euler-Lagrange equation.
No, just stop writing, go back to Zoom. You're going to see the most up-to-date version of what I'm writing. That's the problem. Because if you don't see what I'm writing, then we can't communicate. Do you see what I'm writing on the iPad?
Yeah, I do.
Okay, so just stay on Zoom. So okay, so we have our Lagrange equation. What should our kinetic energy T be?
Well, it should be half. Well, we have two pendulums, so I guess. Well, the two pendulums have different velocities too, so it's going to be a little complicated to. Oh, I know. We can split it up into two different kinetic energies, T1 and T2.
Okay. And so what should I write after that? What should I write if I want to have two separate kinetic energies?
You could write T1 and T2.
Okay, so let me do that. Hide floating meeting controls. So T1 plus T2. Oh, if you really want to write on my screen, then you can annotate on Zoom. That's much better. But of course, you'll have to erase when I tell you to. So okay. So what is my first kinetic energy term gonna be?
Well, our first kinetic term is going to be well, half. Oh, sorry.
Yeah, keep going.
Half m1 v1 squared, and well, yeah, this is obviously can be expressed as a function of theta. So guess I might be able to write it like this, but I'm not sure. And the second one basically looks the same with all of our thingos changed. And by thingos, I guess I mean, I don't know what I mean.
Okay, good. Great. So I'm going to write exactly what you wrote. Please erase it because now I'm going to copy down what you wrote. So half m1 v1 squared plus half m2 v2 squared. Okay, excellent. Now, as our host was saying, we can express these in terms of generalized coordinates. And what are those generalized coordinates going to be? Well, first, let's write down in terms of x and y. So what is v1 in terms of x and y?
Wait, yeah, v1 in terms of x and y is, it's not letting me draw, but okay. Yeah, x dot 1 squared plus y dot 1 squared.
And v2?
Oh, yeah. And also, just want to let you know, don't the two velocities affect each other?
Absolutely. Absolutely. Yeah. And we're going to see that coming through in the Lagrangian equations. So you might notice that I wrote x1 and y1 and x2 and y2 instead of just x and y. And the reason is we need different coordinates for this. We need x coordinate for this guy and x coordinate for this guy. Y coordinate for this guy, y coordinate for this guy. Okay, great. So we've got our kinetic energy, but we've got to express x1 in terms of something better. Let's call this one L1. Let's call this rope length L2. Okay? So tell me what x1, y1, x2, and y2 are going to be. Good. I see you're already drawing what we'll need to define those quantities. So tell me what these are going to be.
Let's draw these real quick. I guess I can call this theta 1 and this small one, theta 2.
Okay.
So now, this thing is going to be obviously L sine. I can't write
very good. Yeah, I forgot. Theta 1. This is theta 1. Thank you. And this one is going to be theta 2. Okay, excellent.
Yeah. All right. So now let me just erase that really quickly because your handwriting with the pen is way better than mine. So now we have L sine theta, and this, not L sine theta, L1 sine theta 1. This is going to be L2 sine theta 2. But the problem is x2 is not just going to be that. X2 is going to be x1 plus the
precisely other. Wow, this is a genius. That's, you see, the first 2 times I did this problem, I didn't even realize that. And so that's a very good point. What about y1? You didn't tell us what y1 would be.
Yeah, just give me a second.
Okay.
So y1, using the same principles, is equal to L1 cosine theta 1.
Okay. Of course, it's pointing down, so I'm going to put a negative on that.
Oh, yeah, that's true. And y2 is negative y1 minus L2 cosine theta 2.
Absolutely. Okay. So I'm going to write down everything you wrote. Just copy it down. So you wrote x2 is x1 plus L2 sine theta 2. So x1 is, of course, L1 sine theta 1. I'm going to zoom out. Is that okay?
Yep, that's fine.
So you should probably delete what you've written. Even though it's exactly correct, I'm just going to zoom out. So there's an option to clear everything, but okay. So x2 is copying down exactly from what our guest wrote. L1 sine theta 1 plus L2 sine theta 2. And of course, y2 is very similar. It's going to be minus L1 cosine theta 1 minus L2 cosine theta 1.
I think that's what you intended to write. Wait, L2 cosine theta 1? Cosine theta 2.
Right. So just checking if you're paying attention right there. So wonderful. So now that we have x1, y1, x2, y2, now we can start getting into the nitty gritty. Believe it or not, this was the easy part. Oh, this was the hard part.
In algebra to come.
Exactly. So now what we're going to do is take the derivatives of these quantities. Okay, so let's take the derivative of x1. What is that going to be?
Let me try.
Sure. Ashish Kumar, while you're writing, said awesome. And Abhishek, thank you for watching. So let's keep on going.
So I'll fit it with your color. And this is the time derivative. So we have L1 theta dot.
Yep.
Yeah. Cosine theta 1. So you could probably write what I just wrote in there. This one is just going to be, I'll just write it as x1 dot because I'm really lazy. Plus,
we have Bishnu Barman saying hello. So let's give a shout out to Bishnu. So
yeah. Theta to the dot cosine theta 2. Okay. I've been laboring hard.
Wonderful. So we have all of our derivatives. Let me check what you wrote down. You wrote x1 dot is equal to, I'm going to start writing over what you did, so you can start erasing it. Even though it's completely correct, L1 theta 1 dot times cosine of theta 1. Y1 dot is, of course, just take the derivative. That's minus sine theta 1 times theta 1 dot. Let's see what you have for x2's derivative. You have x2 dot is equal to, you can start erasing, even though, again, it's completely correct. L1 theta 1 dot cosine theta 1 plus L2 theta 2 dot cosine theta 2. And again, that's exactly what you had. Just for lack of space, we erased it. So I think we're good so far, right?
Yeah.
Any questions so far?
Oh, I just realized we have to square it now.
Now we have to square it, but no fear, everything is near. So
yeah, the end is near. We can't factor out anything because the thetas and the L's are different.
well, actually, it's not as bad as it might seem like. Let's take a look at what our kinetic energy actually is. What is our kinetic energy? This thing right here, right? Okay, so we've got two terms in our kinetic energy, one for the first mass, one for the second mass. So for the first mass, we have x1 dot squared plus y1 dot squared. So what is that going to be? What do you think?
Can I draw it?
Sure. Just write it over here.
Oh, T1 or just T?
T1.
Okay, so let's just draw T1. So now that's going to be half M1 times, it has come. So let me do x1 dot squared. That's going to be, oh yeah, it's going to get worse when we get to x2, but for now it's fine. Cosine squared.
Now you actually don't have to write all of it out. What do you know this? Cosine squared theta 1 and sine squared theta 1 when you add them.
Oh yeah. So just L1 squared theta 1 dot squared.
Exactly. So L1 squared theta 1 dot squared. Okay, you can erase. Oh, thank you. Okay, so now we've got the first kinetic energy. Now we've got to go a little bit to the little bit hard part, which is squaring x2 dot and y2 dot. So we've already got our guest praying for mercy, but of course that's not going to work out. This is Lagrangian mechanics. There was actually a joke that my professor said prayer was banned in colleges due to different policies, and everybody followed it except the day before the exam, or actually the morning of the exam. Then the room would be full of prayer. But anyway, so that gives you some hope. So x2 dot squared, you want to tell me what that is or write it down?
Yeah.
Or you just tell me what this one is. This one is rather long. So L1 squared theta 1 dot squared, or I'll write it out, that's fine.
Theta 1.
Mm-hmm.
That's just the first term of 3 plus 2.
Let me write the square terms first. Is that okay?
Sure, that's fine by me. If you never leave. Plus 2 L1 theta 1 dot theta 2 dot.
Mm-hmm.
Cosine theta 1 cosine theta 2.
See, that's not so bad, is it? Once you write it out, it's perfectly fine. Bishnu Burman. Okay, we're going to ignore that comment. So what about y2? Sorry?
Wow, what a spicy comment it must have been.
Spicy indeed. So I'm going to make some space for us by taking this x2 dot squared and moving it over here, which may be contentious, but I know the comment section is already raging. That's not allowed. How dare you move the x2 dot squared? But that's fine. MD Naman says we are the bright star of. Okay, thank you. So y2 dot squared. Let's go ahead and square that, shall we? L1 squared.
We don't have.
Sorry?
We don't have very supportive comments today.
No, extremely supportive. Thank you to all of our viewers who make possible. So L2 squared theta 2 dot squared sine squared theta 2, and then don't forget the cross term, which is L1 L2. So let me go ahead and delete this over here.
Have mercy. Have mercy.
Well, I'm the one carrying out the calculation.
Oh.
So L1 L2.
I know I'm going to have to do this in just a bit.
Yes. So
That's what all the kids said.
okay. Ashish Kumar says can't see clearly. Well, Ashish, I hope you can see clearly now. So now all we have to do is add these up. Trivial. Trivial, I say. So let me go ahead and duplicate this on another slide. And let's erase some of the simple arithmetic we did.
Yeah.
Because it's just arithmetic, really.
Well, I mean, he's technically not wrong. It is arithmetic.
Exactly. It's just squaring numbers. It's like second grade math.
Yeah. Except it's mundane.
So, okay, now let's add up x2 dot squared and y2 dot squared. Do you see any kind of things that we can exploit? Hint, hint, the things that are highlighted.
Ah. No, I'm just kidding.
Okay, come on.
Okay. I know, we're wrong.
What should I write?
Can you zoom in somewhere?
Yeah.
Because, yeah. All right. So, yeah. Oh, yeah, please zoom in. I'm not good.
That's fine. So I'm just going to write down what you say. So half m2, and then what should I write in the parentheses?
You should write L1 squared, theta 1 dot squared.
Okay. And then do you see anything else? Hint, hint. What is highlighted in green?
Yes, I know, genius.
Okay.
L2 squared, theta dot 2 squared.
Okay.
And then finally, plus.
Okay.
2, L1, L2.
Well, can't we add them up, or oh wait, no, we can't. But can't we factor them out?
Yes, that's what I was going to do, genius.
Okay, and then what goes inside?
Factor.
Yeah, what goes inside the factor parentheses?
Parenthesis. Just draw the parenthesis first.
Okay.
Cosine theta 1, cosine theta 2. Plus sine theta 1, sine theta 2. Wow.
Does this look familiar? Well, our little mathematician must have realized that cosine theta 1 times cosine theta 2 plus sine theta 1 times sine theta 2, what is it? If not, cosine theta 1 minus cosine theta 2.
Oh, you're right.
Ah, you see? All right. Oh, we have a comment from Abhijit Ray who says, hello. So,
wow.
Say it again.
Absolutely beautiful.
Absolutely. What, his comment or the math?
His comment.
Oh, I see. Okay, great. So we've got our kinetic energy. All that's left now is the potential energy, and then we can write down the Lagrangian, and then using the Euler-Lagrange equation, solve for the equations of motion. So if that's not exciting to you, then you're not alive. Okay, so let's keep going. So, okay, so that's T1, that's T2. Let's go ahead and write down the potential energy. What is potential energy? If not, go ahead, say it, our guest. Okay, so our guest is begging for mercy, but go ahead. You tell us, what is potential energy? Okay. All right, so we've muted him. Let's go ahead and write down the potential energies, which is m1gy1 plus m2gy2. And all we really need to do at this point is plug in y1 and y2. And what is y1 and y2 if not what we've written down right here? Y1 is minus L1 cosine theta 1, and y2 is minus L1 cosine theta 1 minus L2 cosine theta 2. So, oh, we've got a comment from Shanahishnoi Roy who says physics is love, man. That's exactly what our guest is saying. So I suppose he's muted or his audio isn't working, but Let's take a look at what our x1 and y1 and y2 were, and we're going to take it right here. So y1 is minus L1 cosine theta 1. So let's write that down. Y1 is minus M1 G L1 cosine theta 1. And what about y2? Can you tell us what I should write for that?
Minus
Yep.
two Z.
Yep.
Wait. Oh, L1 cosine theta 1.
Now this should be a plus right here. And then I should write L1 minus L1 cosine theta 1, and then?
Do that. And then minus L2 cosine theta G.
Exactly. Isn't this trivial? Aruna Baitra is also saying physics is love to me also. So that's great that we're inspiring people to enjoy physics. Really, this is what you should be doing in your sleep. Don't brush your teeth or eat food. Just solve Lagrangians and you should be happy. Now, now that we've got our kinetic and potential energies, all we have to do is write down the Lagrangian, apply the Euler-Lagrange equation, take the appropriate derivatives, and obtain the equations of motion. 4 easy steps. What do you say, our guest?
What?
Okay, so our guest is in another world. So let me go ahead and...
Wait,
Okay, so guest, you tell us what the Lagrangian is going to be. That's our final step. Tell us what the full Lagrangian is going to be for the double pendulum. Go ahead.
Oh, it's going to be half M1 L1 squared theta 1 dot squared plus half M2 parenthesis L1 squared theta dot 1 squared plus L2 squared theta dot 2 squared plus 2L1 L2 theta 1 dot theta 2 dot.
Yeah, you can keep going.
Cosine theta 1 minus theta 2. But we're not done. Minus. Well, actually, no, plus.
He made a mistake. He made a mistake. Yes.
M1 GL1 cosine theta 1. And now I'm going to do something incredibly controversial. Are you ready? I'm going to not do what you wanted me to do.
Okay. What is that?
Plus, yeah, I'm not doing what you want me to do. L1 cosine theta 1 plus L2 cosine theta 2.
Wow. Ladies and gentlemen, what is this if not simplicity? What is this if not beauty? This is a simple 1-inch long equation to describe a chaotic, ergodic, complicated system. I mean, isn't this much easier than Newton's laws of motion? I mean, this is amazing. So this is great. So if you're having fun, ladies and gentlemen, then that's the intended effect.
What?
So
Off myself and do this again.
Right, and Aruna Baitra says that is great to understand. Indeed it is. Indeed it is. Now let's move on to the spherical pendulum. Or actually, I'm going to let our guest decide which system we should analyze next. The spherical pendulum, the cylindrical pendulum, the moving incline, and what if you had a spring pendulum? So go ahead. Our guest, decide what our next problem should be, and our last problem, actually. You decide.
Our next problem should be you. You're the biggest problem of all.
Okay, so our guest has chosen problem 12. Okay. You want this one?
Yeah.
Oh, okay. Our viewer also says second to last. Okay, so it seems like you agree. So let's go ahead and analyze this system. But first, Soborno, can you tell us a little bit about the regular inclined plane? All right, I'll take it from there. So the regular inclined plane, yeah. Please erase what you wrote.
Oh, I did. Yeah, I will. So the inclined plane is basically, obviously, when you have, some sort of angled surface, and then you have a box on it. So most of the time, we consider there to be friction, either static or kinetic, or even both, if you want to be really exotic. Mm-hmm. And in fact, that was one of the simulations that we had at the beginning. Here is a very brief free body diagram.
Now, don't make it complicated. Just explain the basics. No math.
Anyway, yeah.
Okay, great. So that's the basics of the inclined plane. So today we're going to explore the inclined plane with Lagrangian mechanics, but with a little bit of a twist. And that twist is that the inclined plane can actually move. So while the block is sliding down, if the block is heavy enough, the plane can actually slide back while the block is sliding down. So it's actually very interesting. So just imagine that this block is sliding down. What are some of the coordinates that we're going to need? Well, we'll only need two coordinates. The first coordinate is how far is the block along the incline. Let's call that coordinate Q1. And the second... Yeah.
You can let your x-axis be along the surface of the incline and your y-axis be to the perpendicular, which is pretty much what we do with any P class.
Exactly. But now the incline is actually moving, right?
Yep.
So now what I'm going to do is add a second parameter. Can you guess what that is? It's just going to be the distance that the inclined plane moves. Okay?
Wait, why are you Q?
That's what the book uses, so that's the standard convention.
So how can you one variable?
We have a question from Shenahanshu Roy, who asks, will mg sine theta be responsible for its sliding if its magnitude is greater than the friction magnitude? Okay, I'll let our guest handle that.
Wait, what?
Okay, will mg sine theta be responsible for the block sliding if the magnitude of that force is greater than the friction magnitude?
Well, yeah.
Definitely. Yeah.
Let me draw that. Is that fine with you? Can I draw it?
That's fine, but in this problem, I just want to mention we don't have any friction because, to be honest, I don't know how to do Lagrangian mechanics with non-conservative forces. Okay. So
anyway.
But the answer to your question, Mr. Roy, is yes. It should be that, of course, if the gravitational force pulling it down is greater than friction, then the box should accelerate. Yeah.
Wait, Refath.
Yeah.
I just want to know, is there a difference between a ball sliding on an inclined plane and a box sliding on an inclined plane?
Certainly. You see, a ball would only makes contact with the inclined plane along the tangency point, right?
Mm-hmm.
So it would experience much less friction than a box. And also, a ball of the same diameter as a box would have less volume. So you'd also have to consider its, since a ball is rolling, you have to also consider its rolling kinetic energy. Its kinetic energy of rotation. And that kinetic energy is going to take away from the kinetic energy of translation. So at the end of the day, a ball would actually have less velocity when it reaches the ground than a box, right? Because more of the energy goes to rotation, null motion. So
that's great. Oh, I wanted to also ask, can we generalize this for 3D or any n-dimensional system?
Well, what do you mean? What do you mean 3D inclined plane? I don't know.
No, like, what if you had, for example,
Oh,
try.
Shana Hansu Roy says thank you. So you're welcome. Yeah.
Yeah. So what if you had an inclined plane that looks like this?
Mm, well, then I would say that, first of all, why would you analyze that system if it just seems to be a 3D extrusion of the 2D cross section? But yeah, it looks like you're just extruding the system along an axis, and the physics should remain the same because it's symmetric. If you know what I mean, right? If I'm analyzing a circle down, rolling down a inclined plane, it certainly won't be the same. A disk won't be the same as a sphere, but in this case, I believe the physics should remain the same. Okay. So with that being said, we're going to get started with analyzing this system. So of course, the first step is to write down the Lagrangian. So our guest, what is the Lagrangian, just generally?
I'm sorry, Refath, but I just had a revelation about geometry. You know what it was?
Go ahead.
A sphere, a circle to a sphere is just like a square to an octahedron. Any cross section of an octahedron is just a square of some size.
Absolutely, absolutely, yeah. And if you form the net of an octahedron, what is it if not two tetrahedrons put together, right?
Yep.
Right. That's actually how I learned how to draw an octahedron. It's just like this.
Technically, that's a square pyramid, but yeah.
So okay, let's keep on going with our physics. So what exactly should my kinetic energy be?
Well, wouldn't you have to have a separate one for the box and the plane?
Precisely. So for the plane, for the inclined plane, that one is pretty easy. Oh, I didn't tell you what the mass is. So the mass of this is big M, this is small m, okay? So for the inclined plane's kinetic energy, would you believe me if I told you this is the kinetic energy? And if so, how would you justify it?
Hmm. Uh.
Well,
oh, first of all,
yeah.
Wait, 1 second.
Mm-hmm.
First of all, if the square or whatever thing we have was going this way, then the inclined plane would go the opposite direction. No? Right? So, like, if the square was falling this way, wouldn't it push it?
Absolutely.
This way?
What is that if not a consequence of Newton's third law? Right? Amazing.
Uh-huh.
So, okay, you can close it. So that should be the kinetic energy of our big inclined plane. Why? Well, half mv squared, right? Here, v is the velocity of the generalized coordinate q2. Does that make sense?
1 second. Isn't q2 just one dimension?
Yeah, q2 I can just write x2 if that makes you more comfortable.
Wait, but the thing is, then again, do we have to use two separate coordinates?
These two separate coordinates are just kind of like, these are general coordinates because x and y are traditionally in these directions. So these are kind of general coordinates, and we're going to express them in terms of x and y later on. Okay.
Yep.
So Aruna Betra asks, is there any components of small mass? I'm assuming this is a class 11 question. I'm not sure what do you mean by components of small mass. This is an inclined plane, but the plane is moving, and so is the box.
Wait, I have a question.
Yep.
You forgot to specify the angle of the inclined plane.
Oh, you're absolutely right. Wow. Good. Wow. You're okay. So the angle of the inclined plane, let's say it's alpha, right?
Mm-hmm.
So now we're going to express q1 and q2 in terms of our regular x and y coordinates. So let's see if I can do that.
Wait, 1 second.
Yeah.
I think Q2 can just be described as our x coordinate. Meanwhile, Q1 can be described as probably x. Wait, no. It could be described as.
Let me see what we did before. Did we translate x and y to the general coordinates, or vice versa? Let me just take a look. So I believe we
Perhaps we did vice versa.
Yeah, we translated x and y to those coordinates, I think. So let's keep going. Eventually we have to find q1 and q2.
Wait.
Yeah.
Then I have a little bit of a better idea.
Mm-hmm.
You could make the x-axis along the inclined plane, and then the y-axis perpendicular to the inclined plane, and then you can just express Q2 as, if I'm not wrong, x cosine theta.
Well, let me just say what one of our viewers is suggesting. Aruna Betra says m sine theta and m cosine theta. Those are along the right tracks. And Soborno, thank you for your suggestion as well. Let me try out the following. I'm going to say, do you see this Q1 at the top?
Yep.
I'm going to put it right here. Is that all right?
Sure.
So would you agree that this angle is also theta, or would you not?
I would certainly agree, my good fellow.
Right. And so for our x,
yeah. Oh, no, never mind. Yeah.
So the x-axis of our block is going to be q1 cosine theta plus the displacement of the inclined plane, q2. Would you agree?
Oh, yeah, I would.
Interesting, right? Okay. What about y? What do you think?
Wait, that describes the x displacement of the block, no?
Right, exactly. Not the mass. Mass is just obviously q2. That's what this one is for. But we're just doing the block right now. Yeah.
Yeah. So the y coordinate of the block is not affected by the plane. So we can just say, I believe, that it's q1 sine theta.
Absolutely. Absolutely. So q1 sine theta. And you might be saying negative. Did you say negative?
Yeah, I think it should be negative, right?
Right. But I'm going to defy convention and define my y-axis to be downwards. In many circles, this is considered heretical practice. In fact, you would be banned from the American Physical Society if you were found doing this in public. But thankfully, we're not live or anything, so I think we can safely put our y-axis downwards. Okay, so great. So now we have this, and now we're going to take the derivatives of x and y, and then square them, and then put them together to find our velocity, and then incorporate that into our Lagrangian, into our kinetic energy. Then we can write the Lagrangian, and then using the Euler-Lagrange equation, find the equations of motion. Isn't this beautiful, ladies and gentlemen? Okay, so Soborno, by the way, there's a very big surprise waiting at the end of this problem. So if you can solve this problem successfully, there's a huge surprise. Okay.
Is it tough?
Okay. So what is okay, fine. Yes, maybe. What is x dot?
Well, x dot is going to just be well, this is with respect to time, so wait a second, but sorry. Well, theta doesn't change. Theta is the constant here.
Absolutely, absolutely.
So would it not be q1 dot cosine theta plus q2 dot?
Absolutely, that's perfect. You literally couldn't have written out a better answer, because anything else you would have written would have been wrong. So you wrote q1 dot cosine theta. Please erase what you wrote on the top so I can write over it.
Yep.
Okay, we have a question from Snehansu Roy. He says, can you please explain how the y coordinate is q1 sine theta? Okay, so let me try to explain.
Can I?
Yeah, go ahead, explain.
All right, so how is our y coordinate Q1 sine theta. Well, let's take a deeper look at what little Refi boy has over here. So I'm going to draw that on my own. Oh, yeah, he's zooming in for me. Thank you, little Refi boy. So let's erase everything else that I have. So now, due to basic trigonometric rules, we know that this length, by definition, has to be Q1 cosine theta. And this one, since it's the opposite side to theta, has to be Q1 sine theta. And furthermore, little Refi boy, if you paid attention, defined his y-coordinate as being what would be the conventionally negative y-axis. So this is his y-coordinate, this is his x-coordinate. So clearly his y-coordinate has to be Q1 sine theta. Was that a good enough explanation?
Okay, I think that was perfect. Snehansu, if you have any further questions, put them in the chat. Hopefully that explained your question. So let me just highlight his question one more time. And there we go. Okay, so as our guest wrote down just a few seconds ago, but we have limited space, y dot is, what is y dot? If not q1 dot sine theta. Snehansu Roy says, thank you, Soborno. Would you like to? Okay, great. So we have x dot and y dot. So now, remember, we have a kinetic energy for the box and a kinetic energy for the plane, for the inclined plane, right? We've written the kinetic energy for the plane already, right? It's just half big M v squared. V is Q2 dot. But what about the kinetic energy for the small box? Well, let's write it down. It's going to be half small m, because this is the small box, and then v squared, right? Half m v squared.
X dot squared y